Alley cropping. How many of you have seen an alley cropping in practice, like on the landscape? Okay, many of you have seen it. I'll be talking about the ecological interactions or tree crop interactions when you try to put an alley cropping system together. At least that's what Mike wanted me to talk about. So I'm not going to give you any basics about how do you design an alley cropping, but since many of you have seen an alley cropping, you know the context. Most often you are trying to raise or establish an orchard of some sort. It could be a nut orchard or a fruit orchard, or it could be timber trees, or it could be like short rotation woody crops, or in some instances it could be just simply some shrubs. But then you have a lot of space in between. Let's say you are talking about black walnut, for example. You may have to wait for, if it is for nut crops, perhaps 8 years, 9 years, 10 years, and if it is timber, much longer. So during the establishment phase, you could use that land in between the trees to grow another crop. So you could utilize the site resources much better rather than try to control the weeds in between all the time by mowing or applying herbicides. You could grow a second crop. In the tropics, when you look into the history of this kind of alley cropping or intercropping, you would see practices where, at least in India, I know that history very well, the British started this system called, locally known as Tongaya. They were trying to establish high valued timber species. So they would plant, for example, teak, and then of course someone needed to control the weeds. Well, they found a very cheap way to do it, not goats, but the local people. They would lease the ground to the local folks to grow their rice or some other crops, including some leguminous crops or any kind of crop. So the local folks kept it weed free, and of course they would raise the teak plantation. So the first few years until the canopy closed, they could grow their conventional food crops. So there is a lot of potential for alley cropping in the US, as many of you have seen, but perhaps this is one of those underutilized agroforestry systems. Down south, you could see a lot of orchards like pecans. Well, if you go further south, like in Florida, citrus. If you move up here, again, northern pecan, you will see some examples, and I think we have a lunch speaker, you will hear from him. Or it could be black walnut. It could also be chestnuts. The Center for Agroforestry has been talking about Chinese chestnuts, establishing as an orchard. So there is a lot of potential to introduce alley cropping on the landscape. But when you combine species, of course, you have to worry about two sorts of interactions. Competition, most often we think about competition, but there is also the synergistic, complementary interactions that could be beneficial for the system that you establish. I teach a class here called Ecological Principles of Agroforestry. So we cover these topics that I'll be talking about in the next maybe 40 minutes over the course of the semester. So I'm trying to condense down and try to give you at least a little bit of the information. So it's not comprehensive, but at least you will get an appreciation for some of the factors that you need to think about based on examples. So speaking about competitive interactions, there is competition for light, and you heard a lot of discussion about light in the silvopasture talk. competition for water, and then there is competition for nutrients. And when you try to put together some species, there is also another kind of an interference interaction that you need to think of, that is phytotoxicity, or in the ecological literature you will hear the term allelopathy. So we will talk about that also briefly. Again, each one of these topics we can go on for another, like maybe a day or at least 3-4 hours on each one. Speaking of the complementary interactions or synergistic interactions, microclimatic modifications. Forest farming is a good example. The same thing happens in alley cropping because of the modifications in the microenvironment. There could be some beneficial effect on the associated crop. Insect pest control, that has been well established in agroforestry in the temperate region as well as in the tropics. When you mix species together, there can be some positive changes. And most often, some of the herbaceous, like predatory, not predatory, but herbaceous insects will be eaten by some predatory insects. So it's well established. Soil improvement, nutrient capture, and I will talk about only the nutrient capture aspect in this lecture because we don't have time to delve into all these examples. But tomorrow, when I talk about ecosystem services, you will hear a little bit about some of these aspects. So let's start with a good example for alley cropping from the temperate zone, especially from the Midwest, that is black walnut corn alley cropping. This was my PhD research in Indiana. And we had different alley cropping widths that we experimented with by planting either 6 rows of corn or 12 rows of corn in between black walnut trees. And the trees that you are seeing in this picture, they are about 12 years old. So let's start with this system in mind. Well, it's not like very young trees. Well, you can start when you establish these trees, and that's what happened with this system. They started growing corn in between the trees from the very first year when they started the black walnut orchard. Well, I came on board as a PhD student when the system was about 11, 12 years old. And here is another system that you will see mentioned in this talk, that is the Pecan-cotton alley cropping system. When I became a faculty member, this was one of the first trials that I established. And several students finished their degrees, and one of them is sitting right there, Jeremy Zamora. He got his PhD by looking at the interactions in this particular system. So you can see the trees are much bigger, about 50 years old, and you can still see the cotton that is planted underneath is doing excellent. But the trees are, as you can see, with large crown, very little light, a lot of shading. They are 50 years old, but still the system is sustainable. Why? How? We will get into that. So let's start with competition for light. What's going on in these systems and how do you manage that competition? Well, you heard from Dusty and Mark that you could thin the trees, but in a system like this, when you establish only a set number of trees in alley cropping, that often is not an option. So this is what happens, like a 9-year-old, it's a pine alley cropping, but when the trees are about 12 years old, there is not much light coming through the canopy at all. You can say the canopy is pretty much closed. So what happens when you establish an alley cropping? In the tropics, the orientation of your alleys doesn't really matter, because the sun goes through the equator, so it doesn't matter whether you set up your alleys east-west, north-south. Well, even in this room, there will be differing opinion about how do you set that up when you move to the northern hemisphere or the southern hemisphere. Well, if you move to the northern hemisphere, perhaps one of the best ways You could set up your alleys based on your constraints of your land any way you want. But if you look into the principles, if you set up your alley orientation north-south, this is what will happen, what you see here in terms of light. Let me explain that a little bit better. During the middle of the day, you will have this sort of a light distribution pattern throughout your alleys, and this yellow line here. Okay? So I have pretty much the middle row, that is the yellow here. If you have this sort of a configuration, 6 rows of corn, the trees on both sides, north-south orientation. If you look at the middle row is pretty much lit the highest during the middle of the day, but, well, of course, there is a little bit of shading on both sides, but there is no shading during the middle of the day. Let's see what happens in the morning. Okay? The sun is, of course, in the east. The rays will be hitting this tree here. That means the eastern row is going to be shaded, but the sun rays will be hitting the western row, giving plenty of light. So that's what you will see here for the eastern row in red. You can see that there is shading in the morning, but plenty of light in the afternoon when sun is in the west. So, but then the western row, as you can see here, is shaded in the evening, but it is getting plenty of light in the morning, as you can see here. So that's what happens in terms of the light dynamics in the alley cropping system. Now, question for you all: what will happen if the row orientation is east-west? What's going to happen? Let's say this is the equator here, okay? So we are in the northern hemisphere. So we have an alley cropping. So the row orientation is east-west. So what's going to happen now?
Your furthest northern row within the system isn't going to get much sunlight.
Yeah, this part is going to get sunlight pretty much throughout the day, right? Whereas this part is going to be shaded pretty much throughout the day. Whereas in that sort of a configuration, when it is north-south, there will be shading, as you can see there. Eastern row will be shaded in the morning, western will be shaded in the evening, but then it reverses in the afternoon. And the middle row is always getting a good level of sunlight. So overall, if you average the sunlight, it's going to be pretty good throughout compared to the east-west orientation. So most often, this is the orientation that you choose for this reason. But based on your landscape, the constraints that you experience on your land, you may end up putting something like this, and may be willing to go with that sort of a light level distribution. And in some instances, it may not matter much at all. I will get to that in a second here. And here is that scenario. And we will examine two different kinds of crops. In this graph, let's look at corn yield as a function of the light transmittance. Okay? So if you look at, you can see, and this is based on that 12-year-old corn, black walnut alley cropping system. Okay? What's happening here? We had a 12% reduction in light transmittance overall. The trees were young. You saw there was plenty of light coming through the system. Just 12% reduction in light. So what's happening in terms of yield? A 39% reduction in yield. Okay? Keep that in mind. In a young system, with corn, it is already happening. Almost 40% reduction in yield with just 12% reduction in light. It's extremely important. Keep that in mind. Let's look at another system, the one that Jomi studied, the pecan-cotton alley cropping. The trees are much bigger canopy, as you saw in the figure earlier. And if you look at the alley, compare that with the outside, there is a lot more reduction, more than 50-60% reduction in PAR, or the photosynthetically active radiation, the part of the light spectrum that can be utilized for photosynthesis. That's what you refer as PAR. So, a lot more reduction, not just 12%, well, 70% reduction overall in that system. Let's look at the yield reduction. Only 4%. Well, it was not corn, it was cotton. So, even with large trees, 70% reduction in light, that means the canopy is only filtering through, like 30% light falling into the understory, but still you are getting almost the same yield that you would get outside in the open. What's going on here? Well, that's why I would like to borrow Dusty's and Mark Kennedy's. It depends. It depends on the crop, right? It's obvious here. Why is it happening like that? Why one crop, just 12% reduction, you get 40% reduction in yield, 70% reduction in light? Well, just laughing at it, still producing the same yield as outside. So, selection of the crop that goes underneath the canopy is extremely critical. And also it is important to figure out at what stage of that stand you are introducing that species into the understory. If early on, no big deal, but later on you have to really worry about how much light is there and what can be grown underneath. How many of you have had, like, let's say, a crop physiology or a plant physiology class? Many of you. Or a basic ecology class? Almost all of you, I assume. Well, here is what physiologists call as a light response curve. So what it shows is the photosynthetically active radiation, PAR, the spectrum that can be utilized by plants, 400 to 700 nanometer in wavelength. That is what is measured here. And here is the net photosynthesis. I had a picture of Jomi. I think I took that out. I didn't want to embarrass him, but because he was in the field measuring this, almost every day, I guess, at least during a couple of growing seasons. If you look at this, look at where corn, what that plant is doing in terms of its photosynthesis. When you increase the light level, the photosynthetic response is linear. It goes up. Higher the light, better the productivity, or better the photosynthesis. Better rate of carbon fixation, which translates to better yield. What's happening in a C3 plant that is like cotton? So corn is a C4, cotton is a C3. Right about 500, you can see the rate of increase pretty much plateaus. Beyond that, you can keep increasing the sunlight. Well, there is no point. It's not really translating into increased net photosynthesis. That's where it plateaus about at 500, a fourth of the full sun. So 25% sunlight, cotton plants are still going to be okay. And there are a lot of plants like that, where they don't need the full sunlight. So it depends on what you are introducing. So you can tweak the system, and that is one thing that you need to keep in mind. Agroforestry systems are, for the most part, flexible. The design is flexible. It is to suit the needs of the landowner. So the species, you have options. The spacing, you have options. The management practices, you have options. Keep that in mind. You can tweak any of those components and make the system work. and make the system ecologically sustainable for the long run. Otherwise, you will run into problems and your system will be a failure in no time. For example, if someone wants to plant corn between black walnut forever, well, they are set up for failure. You know that. First 10 years, perhaps it works great. Beyond that, change to a C3, try soybean, or maybe try pasture. So you have those options. You need to be flexible so that you can manage the interactions and make the system sustainable. Well, I talked about photosynthetic rate, importance of light, a critical component. But here's another thing, that unit photosynthetic rate is only one component of yield or productivity. That is important. But there is one more factor that is really important, that is the leaf area. What I showed on the y-axis earlier in the light response curve was the net photosynthetic rate per unit leaf area. So you get the picture. That number multiplied by how much leaf do you have in the canopy. That determines the total productivity of that plant, the total yield. So leaf area is important, because canopy photosynthetic rate, that drives the productivity of that plant. And competition for water, the second factor that I would like to discuss. So it brings us to that particular point. And make sure you understand this statement clearly, because there are lots of physiological processes in a plant. But leaf expansion is the first process. It's not the photosynthesis, it's not the respiration, it's leaf expansion that is affected first by water stress in plants. So, what happens if there is competition for water? You saw some large trees in that picture, 47, 50-year-old pecan trees. They take up a lot of water. So you may wonder, how did they grow that cotton underneath? Even with all that competition, they looked really good. Well, there is a trick which I will introduce later. But now let's talk about competition for water. And your gut feeling is right. If you look at the soil moisture, soil water content in the alleys, you will see that with no competition, it's kind of uniform through at least from May through September. With competition, that means trees taking up part of that water, you can see it drops considerably. So there is a big difference. And we separated that competition in some plots by trenching the root systems of the trees and putting a barrier, plastic liner, that separated the root interactions between the trees and crops. And the liner or the barrier went all the way to about 4 feet. So we knew that we successfully, we cannot say eliminated, but at least we can say reduced that root interference, root competition. So with competition, you can see there is less water in the alley for the cotton. But when we isolated that competition, there is plenty of water for the cotton plants throughout the growing season. We saw the same thing with the black walnut corn alley cropping. So there is competition for water. Just based on this figure alone, that's obvious. And even without showing anything like this, you can assume that, yeah, there is competition. But we have data now to prove that, well, indeed, there is competition. So we measured different ways. Or this was using tensiometers. That was using, the earlier figure was the gravimetric moisture. But the same story here. Longer these bars means drier the soil. So there is similar data, but showing a different soil depths all the way to 120 centimeters, 4 feet. The same pattern. the soil is drier when the trees are also taking up water from the alleys, because 47-year-old trees have roots everywhere. And here is that barrier that I talked about. So rooting density is the key. Well, you can trench the trees, 47-year-old trees, and eventually kill them by doing so. Or when you start establishing the orchard, you can begin this practice. What will happen then? You will train the roots. They will start going deeper and deeper and deeper rather than being lateral. Will that affect productivity of the trees? We don't have a lot of data. We don't have a good way of really proving that. Well, I started a trial to look into that with young pine trees down south, but then before I could conclude, I left. The study was abandoned eventually, so we didn't get all the data we expected. I don't think we have a lot of data to prove that the root training will work very well, but at least in theory, it should work very well. Well, the tree roots will eventually find their way behind or below the barrier and come out into the alley. But most active root zone for any crop is the top 30 centimeter. So if we can at least eliminate or reduce the competition in the top 30 centimeter, then you can make these kind of systems work. You can reduce that competition. So you really don't need to even put trench like this to reduce the rooting density. As you can see, this is the distribution of the roots at 3 different depths from trees up to 15 feet. Well, if you put the barrier, there is no live roots, that is, beyond that point. If you start deep disking, maybe up to a foot deep, maybe that's all you need rather than trenching and putting the plastic liner. If you do that every year, chances are the roots will go deeper, and then you can effectively reduce that interference of both crops. Well, studying roots is no easy task. Here is a cool gadget that I used, at least in my experiments in Indiana. It's called Minirhizotron. It's like a small camera, like you do the endoscopy or colonoscopy. You insert that into a plastic tube and you measure the roots, and you can monitor them over time. And there is a good relationship between the Minirhizotron root area and the root biomass, as you can see in this graph here. So there are easy ways of monitoring root systems, and with electronic cameras, tiny ones, being so cheap these days, you would think that people would monitor root systems, but I'm not seeing that, so I don't know all the reasons, but hopefully we will see a lot more below ground interaction studies, because that's something that is needed. We need to know the root distribution patterns of these species and how do they interact in order to really make them sustainable systems. And speaking of, again, coming back to leaf area, what's happening with leaf area when there is water stress? I said that is the first process that is affected by water stress. Again, going back to the Indiana example, corn plants, just drawing your attention to a couple of lines here. Look at this yellow here. And that is row 1, that is the closest row to the tree, but with the barrier. That means there is no root interaction. Compared to row 1 here, without the trench, without the barrier. See the difference here. Big difference in terms of leaf area per plant. Well, that will translate to reduction in yield. And here is again the system with the cotton pecan and a couple of grad students. And they measured the individual plant leaf and then translated that into leaf area. And if you look at the individual leaf area, weeks after emergence, the barrier versus no barrier, again, big difference in terms of leaf expansion and the total leaf area in the canopy. So the picture that I showed earlier, where there was only 4% reduction in yield, even with 70% reduction, in light transmittance, that was kind of deceiving because I did not tell the whole story. If you include the competition for water, well, the yield was much lower. But when we did the trenching, the yield was almost normal to the yield outside. So what does that tell you? Even with 70% reduction, we had almost the same yield by eliminating the below ground interaction for water. So which factor is more important, at least for that particular system? Water. And that is something that we have seen in experiments after experiments after experiments. If you can choose the right species for light, that doesn't mean that you will get a sustainable system. There is something else going on below ground. And if that competition is intense, you better do something about it so that you can have a sustainable system. In this example, what worked very well was the trenching, just separating the root systems. And like I said, in all cases, you cannot really go and trench and create a 4-foot deep trench and plastic barrier. It's not possible. But there are other ways of reducing that competition. It could be by applying herbicides around the trees in a silvopasture system. It could be by deep disking. So it's possible to reduce that competitive factor too. Mike is giving me all sorts of indications that I need to wrap up. But so just to show you some more data, because in agroforestry, you will hear this tomorrow from me again, we used to claim about a lot of different things. Agroforestry can do this, that, and for most of these claims, we didn't have a lot of data. And even for these sort of ecological interactions, we didn't have a lot of data. But now we do have some solid data to show, okay, this is what's going on. If this is happening, you do this, and then you get this result. We can pinpoint where the bottlenecks are and try to make a system work. In the past, we didn't have that. We had to pretty much depend on our gut feeling and trial and error. Well, we do that still, but we also need some data so we can talk to our colleagues in forestry and in agriculture and in horticulture, in pasture, dairy, and we can tell them, look folks, we also have data to prove that these systems can work and do this for you. So we can measure, using different techniques, the soil water uptake in these plants, which we did, just to show that, yeah, there is competition. So if you look at corn water uptake with and without competition, this is the seasonal pattern. And if you look at the growing season total, no competition versus competition. And the red means the black walnut trees were also taking up the water. Otherwise, that water could have gone to probably the corn crop. Look at that, about 26% reduction as a result of competition from 12-year-old trees. So we can pinpoint that, yep, there is that much reduction. That will translate to a big reduction in yield. So you need to do something if you plan to grow corn even when the trees are 12 years old. Do something in terms of reducing that competition and you may get your yield back. The cotton water uptake, if you look at that, there was a 44% reduction, which is expected. The trees were much bigger. You saw those trees, 47 and 50-year-old big trees. A 44% reduction when those trees were competing for the same root zone for the soil water with the cotton crops. Well, I think I went backwards. Competition for nitrogen. So we talked about competition for light, competition for water. We cannot disregard the competition for nutrients, even when you put fertilizer into the system, because there is the competition for that fertilizer between your crop and the trees if you don't eliminate or reduce that interference of the root systems. We used a tracer 15N labeled fertilizer, and that has been done in multiple experiments, and we found similar patterns. This is the natural abundance of that N15. So if you look at corn with barrier, or with barrier, here is it, and without the barrier, and here is the walnut trees. So what you are seeing here is, with the barrier, the walnut trees are not taking up any more nitrogen. As a result, there is no increased abundance of the N15, that is a stable isotope of nitrogen. There is no increase. Well, here, there is that competition between the root systems. You are seeing a little bit of uptake of that nitrogen. Okay? So there is competition. As a result, what's happening in the corn? What would you expect? You would expect when there is no competition, that means when there is barrier, you would expect, wow, you will see a lot more nitrogen taken up in corn compared to no barrier or when there is competition. But that's not what's happening here. Can someone explain to me what's going on here? You are seeing a reduced uptake of the fertilizer nitrogen when there is no competition. That's not what I was hypothesizing, at least as a grad student. I thought when you eliminate the competition, you will have a lot more fertilizer in the plant, in crops, in corn here.
Is there a water interaction?
Well, there is more water now available. So with more water, I would expect a lot more fertilizer taken up. But that's not what's happening. Well, we'll come to that again. Keep that in mind. Keep thinking. We'll come to that in a second here. So let me see again total nitrogen taken up in the plant. Okay? If you look at the grain and the stover, the grain here, the stover here, with and without competition, this is the total nitrogen, not just the fertilizer nitrogen. Okay? You have a lot more, 40% higher nitrogen without the competition, 41% nitrogen without the competition in stover. So there is a lot more nitrogen in the whole thing, but less fertilizer nitrogen taken up when there is no competition. And here is the nitrogen derived from fertilizer, another indicator to give the same story. Grain and stover, again, in both components we saw, without competition, less fertilizer nitrogen. What's going on here? Well, this also depends when you plant the crop. In Indiana, when do you think the farmers will plant corn? May? End of April, May. And if it is too wet, yeah, whenever they can get in. And this particular year, I think it was planted late, like maybe May or even early June, maybe late May, I would say. So what's happening by then in terms of like the trees, the black walnut? Yeah, they are transpiring. They are already leafed out, right? Not fully leafed out perhaps, but still mostly leafed out. Well, they take most of their nitrogen early from the available pool of nitrogen in the soil. So when there is competition, the nitrogen that is already in the soil is already taken up, most of it, by the trees. So the corn grown in that area had to depend on a lot more nitrogen from the fertilizer. When we eliminated that interference between the root systems, the trees did not take up that nitrogen early in the season from the alley where you put the corn. So the residual nitrogen in the soil stayed in the soil. So a lot of natural nitrogen plus the fertilizer nitrogen. Well, the plants didn't have to depend on the fertilizer nitrogen that much. So although I couldn't prove my hypothesis the way I wanted to prove, after discussing with maybe about 5 different agronomy professors, we found the explanation for what was going on. So that still proved that there was competition. So it depended on the timing. Well, we saw similar things happening when we experimented with cotton and pine down south. So, well, this is fertilizer use efficiency. As a result of that competition, if you look at the fertilizer, well, you are putting a lot of money in the fertilizer. That's where it is important that you get the fertilizer where you want it, in the crop. If you look at the use efficiency, with no competition, it is much higher fertilizer use efficiency compared to with competition? Well, I would like to make a couple of more points, and hopefully I can finish just in time. So if you look at trees taking up nutrients, well, from a competition point of view, that's a bad thing. But from an environmental point of view, it could be a good thing. So how much of that apply? Let's say we put in 150 pounds of nitrogen per year for growing corn. What proportion of that is taken up by, by corn every year? It depends. Give me a minimum and a maximum.
1 to 99%.
Oh, that's too broad. Well, it could be very well true, but not 99 though. What is the maximum that you would say?
60%. 70%.
Well, most crops, including corn, can take up maybe 45 to 50. Okay? So what happens to the rest 50% of the nitrogen? Well, some of it will be volatilized.
Into another growing plant.
What's that?
It leaches or goes into another growing plant.
Yeah, most of it on a monoculture large 1,000-acre farm, what happens? It goes down. It ends up in our groundwater. Some of it will be, of course, volatilized or denitrification, but most of it will leach down. Okay? So if you have an alley cropping or a riparian zone or a windbreak, this is what happens. The rest 50% that goes down will be taken up by this network of the tree roots beneath the crop rooting zone. And we call it as the safety net role of tree roots in agroforestry. So they will take up, well, it's not the whole thing, but at least a good portion of the leached nitrate, and will bring it up to the trees. And then what happens? Goes into the leaf area, and if it is a deciduous species, what happens? In the fall, it returns to the top of the, the soil. So helps in better nutrient cycling overall in that system, making the system in the long run perhaps less dependent on fertilizer nitrogen, making the system a low input system in the long run.
So is this based on kind of a traditional fall anhydrous application or a different type of more novel spring application of N?
Well, this is based on the conventional. It can be based on the studies. I will show you some data based on just one-time application in late spring, well, right after planting. But in some applications, it is like split applications. And I don't have data from split applications and looking at the efficiency of, uptake.
Fall, it's even less.
Well, if you put in the fall, well, more of leaching, exactly. The trees are, if it is early in the, the season, then the tree will uptake a lot more. And I showed earlier that they will leaf out by May, June. So that's when they need most of that nitrogen. Well, for anything like Dusty says, it depends. Even for trees, depending on, different timing in their phenological events, they could use more nitrogen, even later in the season. But in the fall, well, for most crops, for most tree crops, not much use. So ideally, go ahead.
I was just going to say, NRCS is in cover crops a lot right now, and I would think in any system, cover crops would be ideal for these
Nutrient
corn
take up, yeah,
rotations.
exactly. I agree with that completely. We also have at least 2 major cover crop projects going on, and so you're absolutely right, yeah. So ideally, again, I don't have much time left, you should have spatial root distribution like this in the soil, where one crop should have perhaps less root length density in the top soil and a lot more in the deeper soils, like a tree crop. Well, these are both trees, by the way, but this is a pine, longleaf pine from the south, which I studied quite a bit, so I had the data. And here, well, Jomi helped me compile this data too. This one is sycamore, a hardwood species. You can see there is good spatial separation Well, here it is very low in the topsoil, but here it is very high, the root length density, but lower in the deeper horizons. So if you mix a species, or if you create a species combination like this, well, they work together very well. So ideally, if you have a crop like this and a tree like this, that system can have ecological sustainability in the long run, because they won't be competing too much for resources, at least in the same niche within the soil. So now that will lead to a much better nutrient retention cycling within the system. So here is again just an example from data, or using data from, well, these are based on a couple of studies, but let me summarize what you are seeing here in the next slide through an animation here. So if you look at the distribution of the nitrogen in the soil, okay, without the trees, like a monoculture corn field, you have this sort of a distribution. Within the top 60 centimeter, most of that nitrogen is gone, taken up by the plant. But then if you look deeper than that, you will see that, well, a lot of that nitrogen got leached down into the deeper layers of the soil all the way up to 120. Well, we only measured up to 120, but it could go even deeper and end up in the groundwater. Now let's look at a scenario where you had the trees and the tree roots in this deeper horizon. Well, by the way, this is actual data. Okay, so we observed this in the field.
Were those tiled systems?
No, not tile systems. Look what's happening now. It's uniformly low by the end of the growing season. There is a little bit of nitrogen in the system, but nothing like this. You don't see this bulge. So, in other words, by introducing trees, you could eliminate that much nitrogen going into the soil and then into the groundwater eventually. So, a much better ecologically friendly way of farming, I would say. Yes?
One point, when farmers see a 39% reduction in yield, how do farmers mitigate that? I need to apply more nitrogen now. So now, I mean, you actually have the same problem.
Yeah, and that's where, again, that's where it's not all about nitrogen. You need to keep that in mind. There are, like I said, the competition for light and competition for water. And if you can eliminate the competition for water, essentially, as I showed in two different examples with a C3 and a C4, you could bring that crop yield back. Well, there is always a compromise. Agroforestry is not always about maximizing the yield. It is about optimizing the yield for that particular system. So there may be an element there where they need to care about perhaps something else also, like, well, corn yield, what is the acceptable yield? They have to decide that. And if it is a young system, maybe up to 10 years of that orchard establishment, they may get 100% of the yield like they get outside if they do a little bit of the management interventions, like the trenching or disking or maybe even fertilizer management, they can get the yield. But at some point they have to realize that if that is my goal, probably that's not going to happen. Am I willing to go with 80% and have my trees? Well, if you look at the total economics of the system, Larry will talk about that later, you will see that perhaps you are still making more money than just a monoculture corn, even with perhaps 25% reduction in corn yield, because you have your trees, you have your nuts, or you have your timber. So there are other aspects of that system that provide you with an income. Or if there are either cost share or markets for ecosystem services, like cleaning up the water, or sequestering carbon, or providing wildlife habitat, then you are stacking all your payments. And the system may end up being much better than your monoculture system. So there are, again, we are just talking about just a simple dimension here. But keep that in mind. In agroforestry, you need to think about all these multiple dimensions, and of course, what the landowner wants ultimately. So it's not just, again, that's where the difficulty is in agroforestry. It's not that simple or linear, any of the things we talk about. It's much more complicated. Well, I'm just flipping through this, and I will mention one more thing, the phytotoxicity or allelopathic interactions. When you deal with a species like black walnut or pecan, there is this chemical there called Juglone. How many of you have heard of that? All right, very good. I don't have to spend a lot of time on it. Well, what can it do to associated crops like corn or soybean? Well, let me take you through how much Juglone do you see in the soil, first of all. This is again based on the 12-year-old orchard that I studied in Indiana. You can see that the highest concentration right at the base of the tree, but it goes down as you move away. But still, there is considerable amount of Juglone even about 15 feet away from the tree. That is the message. Even in a 12-year-old plantation, you have considerable amount of Juglone in the soil at different depths. The highest, of course, is in the top, but then it goes down. So if you look at corn and soybean, do they have an effect if you grow them in a black walnut alley cropping? Yes, they do. This is the highest concentration that we applied. Well, we did not find that level of Juglone in the soil, but this amount, 10 to the power minus 5 molar, well, that was present in the soil. Even about 12 feet away, we had that much Juglone in the soil. So if you have that much Juglone in the soil, well, this is what you will see in terms of, this is the shoot growth. You can see that in corn, it is affected. Well, soybean is also perhaps even more sensitive to Juglone than corn. But there is that sensitivity. Your yield can be reduced as a result of that interference interaction with that particular chemical. And then there are other examples of herbaceous plants causing phytotoxicity to tree species, and tree species causing this sort of effects on crop plants. Something that we need to think about before you pick your species to create an agroforestry system. And even for cotton plants, I think the picture tells the story. The same concentrations, and this is the control here, and here is the highest concentration. You can see the difference in growth when you grow in a solution culture. So there is that interference interaction as a result of that phytotoxic chemical in the soil. Can we reduce that interference through management? Yes, we can. Like, for example, by the way, this is peanut. We're not seeing that drastic of an effect on peanut here. When we had the trench, look at what's happening beyond the trench. The concentration of Juglone in the soil dropped considerably. So this is the distance where we had the trench in the black walnut corn alley cropping. So if you had the trench and the barrier, look at this red line. That means the live roots in the soil. So what you can see here is, well, we hypothesized that this wouldn't change much beyond the trench because there was a lot of foliage on the surface. As you know, black walnut sheds all of its leaves, and of course the nuts, everything into the alley. And every component is full of Juglone. So we knew that there would be Juglone, at least in the surface soil. Well, we didn't find it. What happened to all that Juglone? Yeah, it was disintegrated, oxidized to a non-toxic form. So what we found was you have to have live roots constantly producing that chemical in the soil in order to have that soil or in order to have the presence of Juglone in the soil. So if we didn't have live roots, well, it came down to almost zero. So by trenching or by eliminating the live roots, you can reduce the interference interaction from chemicals like this. Well, that's where I will stop. I have listed some publications here that came from many of these experiments. So if you are interested in learning more about any of the things that we discussed, you can delve into the literature. There are some synthesis papers here, like this one particularly here, that talks about all these interactions in a summary form, but then there are individual studies also listed here. And I know I'm standing between you and lunch, so I don't know if Mike is going to leave us any time for questions. Probably not.
I was going to ask that last part about denitrification. So that's like the basis for these saturated buffers. Are you involved with that at all? And are there certain tree species that do better than others in that, with that?
In reducing denitrification?
Increasing, yeah, the denitrification.
Or increasing denitrification? Well, anytime when you have saturated soil, that is certain to happen. Denitrification will happen. But the way to minimize that is to minimize the amount of nitrogen in the soil, in that saturated zone. And by growing fast-growing species like, let's say, willow or cottonwood, you will take up a lot more of that nitrogen, and by that way, you can reduce the amount of nitrogen coming out through denitrification. There has to be a mechanism pumping that nitrogen into the plant. Any other two questions? All right. Thank you.
Couple of quick housekeeping things.